He kōna ipurangi tēnei nā te reo irirangi o Aotearoa.
They say life is stranger than fiction.
So it's about a tennis ball size atom, and then around that you see the electrons orbiting as you would sort of imagine what an atom looks like if you haven't got a chemistry degree, because that sort of orbit is actually unstable.
But sometimes what we see in movies or read in books is so incredible that it obviously couldn't be possible. Or could it? It's so big that it's got thousands of protons.
Thousands is a small understatement. It'd be 2.6 times 10 to the 41. So something with 41 zeros after it.
Welcome to Sci-fi, Sci-Fact. I'm Brian Crump, and this is a podcast where we take science fiction's strangest ideas, weirdest elements, most unfeasible plot drivers, and explore if they could actually happen in real life. Maybe they already have. And in every episode, we bring in a scientist from New Zealand's MacDiarmid Institute to explain the theories behind some of fiction's more fantastic flights of fancy, if any theory exists. In this episode, Dr. Nate Davis, Associate Investigator with the MacDiarmid Institute and Senior Lecturer in Physical Chemistry at Victoria University of Wellington, tells us all about Jumbonium, a plot device from the Futurama episode The Lesser of Two Evils. It's an atom so big, you could wear it on your head.
Good news, everyone. Report to my bedroom for a private exhibition. Everyone, get in bed with me. I have something to show you. Feast your eyes on this.
It's beautiful.
And huge.
Can I touch it?
So what is it already?
It's a single atom of Jumbonium, an element so rare the nucleus alone is worth more than $50,000.
How much more?
100,000. That's why I hid it here under my mattress.
Professor, can we discuss this somewhere else?
Why, certainly.
Jumbonium. Now, I'm not such a... Futurama I like, but I've never got hooked on it. But I know it's kind of like The Simpsons in the future, sort of. Maybe not.
Yes.
Probably tells you how little I know about Futurama. But some of the characters look similar. And Jumbonium is what is Jumbonium? It sounds like an element.
Yeah, so Jumbonium is basically a large atom. So it's in the episode, it's the award for the winner of the Miss Universe competition in the year 3001.
They still had those kind of competitions then?
Yeah, apparently they do.
Right.
But in this case, instead of
so much for women's lib.
Earth, there's people from all around the galaxy. I think the winner's actually like an amoeba-like alien. So it's a bit more diverse than the current competition.
A bit more inclusive, aliens. I hope.
Yes. And Jumbonium is this large atom that Professor Farnsworth, one of the main characters, says that it's worth $200,000 or at least, and it's somewhere between $200,000 and $201,000. So it's quite the prize to be won.
Right. And what does Jumbonium do? I mean, it's a giant atom, so I'm assumed it's connected to other giant atoms.
Actually, it just sort of floats there as a single giant atom. It's big enough that you can see, so it's about a tennis ball size atom. And then around that, you see the electrons orbiting as you would sort of imagine what an atom looks like if you haven't got a chemistry degree, because that sort of orbit is actually unstable. But the basic picture of an atom in a cartoon works very well.
How often do you see pictures of atoms, Nathaniel, and think, that's not how they are?
I mean, every atom I've ever seen, I think, that hasn't been in a textbook or at a conference is always incorrect.
I mean, that's a great big tangent. We could go flying off right there, but I'll try and keep to your script here, Nathaniel. Yeah. I'm assuming that the application of Jumbonium is purely cosmetic. That's what it's used for?
Yes. Well, it might have some interesting properties if you could make it. But all we go from is like a 1-minute scene in Futurama where it's a prize. So let's go with cosmetic because it's hard to predict elements' properties and it's hard to predict fictional elements' properties. But we're going to try and do that along the way.
An atom the size of a tennis ball.
Yes.
And you can not only see, you can see, and I've got an illustration in front of me, which we will have up on our webpage for anyone who wants to check out Jumbonium. Lots of pretty little balls, all squelched together. Now, those will be what, the protons?
Yes. So the actual picture is quite good of the structure of a nucleus. So the center of an atom contains protons and neutrons all squished together.
Are the different colours protons and neutrons, or are the protons and neutrons about the same size?
Yep, they're the same size. In this picture, there's 4 different colours, and that gets a bit confusing. So maybe there's some antimatter there, but if it was there, it'd be annihilating and exploding. So we're going to kind of ignore the 4 colours because...
Well, I'm colourblind anyway, so, if you told me there are only 3, I'd believe you because I can't see the difference between the green and the red.
Oh, perfect. But there are other things that aren't protons and neutrons, which make up protons and neutrons, which are different types of quarks. But that gets really quite complicated and isn't quite necessarily needed for the story of what this could become.
But with Jumbonium, not only do we have the nucleus, we have the electrons spinning around, although I can only see 2 of them. Which would make it
in
helium.
my picture, there's 3.
Yeah. Oh, yeah. Hang on. 3, 1, 2. Yeah, 3. So that would make it. What's number 3? Is it lithium?
Is it lithium?
Yeah, I think it's lithium.
Yeah, that's what I'll guess.
Yeah. It's good on you, good on your chemistry professor.
Yeah, I can look it up. That's the best way to.
Yeah, you're so right there. My son used to had this one of the periodic table songs he memorized for a bit. But I can't remember the tune, so I'm no help to you. But I think it's lithium.
I know there is a song, but I also haven't learned it.
Yeah. But anyway, those electrons, however, they're too close, aren't they, to this nucleus? They should be way out of the shot, shouldn't they?
It depends. So the electrons are meant to be about 100,000 times further away from the the center of the nucleus than the radius. But as they get bigger, because they have to move faster, if you imagine this orbit around a central point, they actually get heavier. So the old equation E equals mc squared, as you sort of approach the speed of light, your mass increases. And then they actually contract in. So having big electrons far away kind of doesn't make sense because the fact that they're big and far away means it'd actually be closer because they'd be heavier and getting pulled in more.
So that's not so implausible after all.
Yeah, so that's sort of okay. The main implausibility is just the size. So I did a quick calculation. If you have an atom, so a normal atom is between about 5 femtometers. And so helium is about 1.6. Uranium is about 15. So
sorry, Nathaniel, sorry to interrupt. You said an atom is how many? What was it? Did you say femtometers?
Let's call it 6 femtometers. Yeah.
What's a femtometer?
So it's 10 to the million of meter. The easiest way to think of it is if you have an atom and a tennis ball, the same comparison between that size difference is a tennis ball and then a large object in space, which is radius is out to around about Jupiter. So all of the solar system is one big star out to where Jupiter's radius is. That's the same size comparison to a tennis ball to an atom.
Okay, right.
So it's very, very, very small.
Those kind of mind-blowing sorts of dimensions.
Yeah,
yes,
so the scale's about 10 to the 13 times is what we're looking at, which is so small that when you start doing the maths, you get into some weird ideas just of how many protons and neutrons you would need to make this material.
Anyway, getting back, sorry, I threw you off course there. You're saying that the size of this atom is what? So what's the problem about having something this big in terms of implausibility?
So just in terms of stability, nuclear stability, there's about 9,000 nucleuses that we know of, or that we can predict. 3,000 were found, but only 195 of them are stable. And it's because the protons and the neutrons are stuck together with a strong nuclear force, but they're also the protons are pushing each other away because they're both positive. And as you get bigger, the pushing away force scales more, so it stays there, whereas the strong nuclear force weakens. So the bigger you get, the more the protons want to push each other apart until they actually do, and your atom falls apart.
Is that why there's a limit to how big atoms can be in terms of the number of electrons and protons and neutrons?
Yep, exactly. And anything higher than atomic number 82, which is lead, is actually unstable. And that's where we get radioactivity. Radioactivity is the protons either tunneling away from each other or becoming small nucleoids and ejecting out of the nucleus as well. So it's all to do with the trade-off between the strong nuclear force and electrostatic repulsion.
The strong nuclear force then is what holds the nucleus together. Like you were saying, the protons are all positively charged, and most times the same charge repels, but this force holds it together. Where does that force come from?
That's a bit deeper than I was planning to go.
I'm sorry about that, Nathaniel, but I mean, what stops everything from just blowing apart?
So it's mainly, if you think of it as like a stickiness, it's to do with some quite complicated quantum mechanics.
I bet it is.
But effectively, just think about if you had a bunch of magnets that were repelling each other, but imagine they only had one side. So again, that's hard. But then gluing them together, and you could find that you could have a glue that would be strong enough to hold them together, but the more and more magnets you have would slowly be stronger than the glue. And that's what's happening there.
Well, that's an analogy I can sort of get my head around. What's the weak nuclear force?
I'm not 100% sure because I am a synthetic chemist, not a nuclear chemist. But the best thing about doing this over Zoom,
away you go,
is I can just.
I love it when I get you guys Googling. I could start Googling myself, but I'll probably end up with something that's not much use.
I've also found something that's not much use.
Because what are the
part of nuclear fission?
I thought it was something to do with the decay of elements.
So that's what nuclear fission is. So it's the weak nuclear force mechanism interaction between subatomic particles that's responsible for radioactive decay.
Right. So does the weak nuclear force play a part in everything? Say, because you were talking about lead. What's that, number 82 on the periodic table?
82, yes.
Beyond that, does the weak nuclear force begin to override the strong and things naturally just start falling off of a man?
I think it's more so that I think the weak nuclear force is more to do with once it's started, the way it decays, in what type of decay you have. But the actual mechanism of decay comes from the increase in electrostatic or at least from my quick understanding of Googling it now, it looks like it's the electrostatic interaction that causes it to break down. And then that's the way it breaks down is described by the weak nuclear force.
But we have a problem with atoms that get to a certain size. They just won't stick together. And Jumbonium is well and truly... Is it... I mean, the thing about there's a couple of ways to look at Jumbonium, at least that come to mind. One is that it's this giant atom and it's got thousands. It's so big that it's got thousands of protons and electrons, and that's why it's so big.
Thousands is a very small understatement. So if it's actually that big, it'd be 2.6 times 10 to the 41. So something with 41 zeros after it is how many protons and neutrons you'd actually have.
Just imagine the kind of decay you get off that thing.
Yeah.
You wouldn't want to be anywhere near it, would you? What sort of gamma radiation is going to be coming off that?
It would be, the biggest thing would be beta radiation, which is small helium particles. So 2 neutrons, 2 protons. And they would stream off that. I mean, there'd be gamma, there'd be everything coming off this in every direction if it was made.
The moment Miss Universe 3001 was crowned, that everyone and the winner would be dead, right, from radiation poisoning.
Yeah, even if it was stable. Later, once we talk about stability, we'll move on hopefully to neutron stars, which is a feasible thing it is, and she'd die from many other reasons than just radiation.
Okay, that's one thing. The other thing was what if you could have an atom where the actual protons and neutrons were large enough to see?
So that's another thing, and there's some ways where people think that if you using higher order dimensions of the ways that you're sort of representing these atoms and the way that you're what's the word? Extending them in, you could sort of maybe push these protons and neutrons into high order dimensions. They could be viewed as larger in our free dimensions. But again, that's stuff, not only stuff that's complicated, stuff that hasn't even been done yet. So it's all theorized, and a lot of it probably isn't really feasible at all to make the nucleus look that big.
However, what we have been able to do, us humans, is make atoms, big ones, bigger than... What's the largest atom in terms of on the periodic table that exists in the natural world?
In the natural world, depends if it's stable or...
Even unstable. Oh, what's uranium? Is it higher than lead on the periodic table?
Yep, it's higher than lead. I'll just get uranium. Atomic number.
If anyone knows the
song. Number 92. So 10 more than uranium.
And we've made things that are much larger than that.
Yeah, we've gone up to 118 from ish. I mean, this is the latest paper I got. I don't know what people have done in the last couple of days, but 118 is a named element. And they've made less than 100 atoms of that. So maybe around 10 atoms of 118 have been made, and it lived for about 1.1 microseconds.
Right. That's a very short life.
Yeah. And the main thing is, because as we get bigger, they become more unstable. There is predictions that there's this area of stability deeper into the periodic table that we haven't got to using our particle accelerators to make these atoms, but they're still going to be orders of magnitude smaller. I think the island of stability is sort of around 100 and maybe 126 protons, and so that's only 8 more than we're at now, and we're nowhere near the 10 to the 41 protons we need to see it.
Organessian at 118 lasts for 1.15 milliseconds. But what do you mean by this island of stability with things that are even larger, have even more protons and neutrons?
It has one of the best terms in science, I think, called a magic number. And so imagine you're packing spheres or marbles together. A certain number of them would pack really nicely together into like another lithosphere. And that's sort of like a region of stability. It's to do with energy shells, and it's a bit more complicated than packing, but packing is a nice way to imagine it. And so the numbers I think they go like 2, 6, 8, and they increase up to about 126 or 128, depending if you're a proton or a neutron. And they're the magic numbers that are meant to be more stable. Oh, here they are: 2, 8, 20, 28, 50, 82, 126. So these are numbers where your marbles can pack together in a nice way, and they're stable.
How stable is stable, though? Are we talking about can hang around? Or
stable enough that if you're a scientist, you'd be pretty excited, but not stable enough that if you owned one, you would think it was a good investment.
Right.
Some of them last like a year. A year would be, for a half-life, would be pretty exciting.
But this is only in theory at the moment, right?
Yeah. They think maybe 100 years for some of them. The problem is...
What sort of properties would they have?
So they'd be very radioactive. They would be heavy. That's sort of all. They wouldn't do too much chemistry, because a lot of these big things, as we talked about electrons getting denser, the orbitals and the new chemistry you can do with larger atoms sort of decreases, because all the big electrons collapse into the shell. And so it doesn't really, it's not so different from the other elements, because it's just like a slightly denser one. Whereas smaller elements, like the difference between hydrogen and helium, one bonds with everything and one doesn't bond at all. So there's like more going on in the smaller atoms.
Apart from maybe getting some kudos, would we be able to use these super elements for anything, super large elements?
No, I don't think so. There might be ways you could make exotic forms of matter or something, but again, it'd be mainly kudos. And they're also very, very expensive to make. So Jumbonium was quoted as being $200,000. These things are built on $100 million facilities with sort of millions, $10 million research budget. Like every one of them costs an outrageous amount of money to make single atoms of it. I think they're some of the most expensive materials in the world. If you compare how much they were paid for how much you got out of it, it's orders and orders of magnitude more expensive than anything we could imagine, like gold or silver or something.
Getting back to the Futurama realization of Jumbonium, and you pointing out that that's not what an atom looks like anyway. I mean, the protons and neutrons don't look like balls, do they? The electrons don't look like balls. I mean, do they look like anything? Are they even particles?
Well, so they're both particles and waves. You've just touched on a thing called wave-particle duality. Everything is a wave and a particle, but when you're small, it becomes more apparent. So a neutron and a proton probably are a sort of spherical little particle, whereas an electron, while as a particle, is more of a wave, and it exists in a big probability distribution around your central nucleus. So you can't really picture that so much as a classic particle because it's so small.
How much of your atom is empty space?
99.999.
Because
if you imagine...
Even the really big ones, which you said maybe the electrons would orbit more closely, the larger the nucleus is?
It's still, because if you imagine, so the electrons are normally 100,000 times further away from the nucleus, and the nucleus is about a couple of say a femtometer, whereas the atom itself is about an angstrom. So it's just orders of magnitude bigger with the electron cloud, and the electron cloud is effectively free space because it's electrons, so they're not really consistently solid.
So you pretty much debunked the whole Jumbonium plausibility, Nathaniel, but you mentioned something else halfway through the interview, and you wanted to talk about it. Neutron stars.
Neutron stars.
What are they?
So it's the only thing that seems plausible to have something that big. So a neutron star is a type of collapsed star, and it's when your star wasn't big enough to form a black hole, but it was pretty close to doing it. So what happens is all the matter collapses in, and it pushes all the protons, the neutrons, and the electrons into each other. And the electrons combine with the protons and make a neutron. And you're just left with a ball of neutrons.
Right.
It has the density of an atom, of the nucleus of an atom. It's effectively like a large atom. It has a lot of the properties of atoms. It's a visible thing now. These are sort of normally around 10 kilometers large. Any bigger, they collapse under their own weight and become a black hole. And any smaller, the neutrons push each other apart and it explodes.
And the neutron star is so dense that a cupful of this or a teaspoonful would be what? The weight of planet Earth or something like that?
So that they calculate that a teaspoon's the equivalent of 900 pyramids of Giza. So it's 5.5 times 10 to the 12 kilograms.
You can really pack them in, can't you?
Yeah. And so if we used our tennis ball size of a neutron star, that's the equivalent to 14 billion tons, which is 5 cubic meters of the Earth's crust. So if you dug 5 1 by 1 by 1 kilometer, or 5 cubic kilometers, 1 by 1 kilometer holes in the Earth, that would be as much dirt would weigh as much as our tennis ball.
What would this stuff look like?
So it's hard to know what they look like because the gravity is so strong and we've never been close to one. But it would probably just look like a shiny, I'm guessing, ball of matter because it's so dense, the electrons are packed in. It's hard to know because we haven't visually seen one. We've only seen them with telescopes through space, and they look a bit like shiny dots, like lots of things in space do.
And does it still? They still emit a huge amount of radiation. You couldn't. So assume you could withstand the gravity, and I'm imagining we couldn't. But if we could, would we still be roasted?
Yeah. So not in terms of radiation. They're actually quite stable, but they've got magnetic fields that are 100 million to sort of a quadrillion times stronger than Earth. So the magnetic field would rip things apart. The gravity on them are about 200 billion times Earth's gravity. So they're very, very scary things, even when they're small.
Could you ever remove a piece of a neutron star, say something so really, really small, but so small that we were able to physically carry it, once it was separated from the star and was no longer subject to the same pressures, what would happen to it?
I would explode if you had a small amount, because the gravity is no longer holding it together. So the neutrons would just push it apart, and that would release. A teaspoon would be easily probably more energy than all of the nuclear weapons we've used today, I'd say.
Even if the winner of Miss
magnitude.
Universe 3001 was crowned with a bit of neutronium rather than Jumbonium, it'd still be fatal.
Yes. And the worst is if you touched it. So I didn't have to do this calculation, which is nice. It's from Randall Munro, who's the person who does XKDC. He had a what if book, and it's really interesting. Everyone should read it. It's scientific answers to absurd hypothetical questions. And the question was, what if we had a neutron star bullet? And so I scaled some of the calculations to be a tennis ball, but effectively, if you just dropped it on the ground, it would smash through the Earth's crust, vaporizing everything as it went down to the core. And then it would sit there and just do nothing until the sun enveloped the Earth, and it'd sit in the center of the sun because it's not big enough if it was stable. But if you somehow put it on the Earth and walked up to it, as you got, say, 2 meters away, you'd feel like you're standing on a hill, like a slope down towards it. As you got within a meter, you'd start sliding towards it. If you put your hand within 20 centimeters, that's the point of no return. It would suck your hand in more than you could pull it away. And then once you actually touch the surface, it would suck your blood to the tips of your fingers. It would burst them because of the blood pressure, and then siphon your blood out onto the neutron star. So you never want to get actually close to touching the surface of these things because the gravity is so strong.
Are there any stars called Dracula?
Mate, there should be. There should be.
Wouldn't it warp space-time if you got close to it as well? Wouldn't your hand end up being in a different time zone to your head?
So technically, yes, because everything warps space-time. But it's not going to be that strong because it's still quite small. Its gravity is strong per its area, but its gravity is not necessarily, it's still not as heavy as the Earth is. Yeah. So it wouldn't warp it as much as the Earth does.
I was just trying to be an optimist here and thinking, I might be losing all my blood, but my head's a couple of years behind my fingers, so I'm not feeling any pain right now.
You don't know it yet, yeah. That happens with black holes, or they predict stuff like that would happen with black holes. But a small neutron star wouldn't be too bad. A big one would definitely do it.
Thanks for listening to this episode of Sci-Fi Sci-Fact with me, Brian Crump. And thanks to our brilliant friends at the McDiarmid Institute. Sci-Fi Sci-Fact is available on the RNZ website, Apple Podcasts, Spotify, iHeartRadio, or anywhere you get your podcasts from. There are plenty of other RNZ podcasts to listen out for too, like the award-winning Black Sheep. And you can catch more of me every weeknight on RNZ National.